Okay, so welcome back. And so this is section 2.1. I know that we have been talking about section 2 for some time now, but this is actually the first real lesson on section 2.1, which is Introduction to Vectors in 2- and 3-dimensional spaces. So, and you may have already, seen vectors. These look like arrows, and you know how to add, subtract, do scalar multiplication on these things. You can draw them, and you can do certain operations like normalization. So these are like the real basic stuff that will be that we will be studying throughout the course. And so pay close attention, and I'll be sharing the screen in just a second. Here you go. All right, so your first two first two pages should be done by now. We go into the proper part of section 2.1, and so these are the vectors, and they take place in real spaces. Let's talk about what a real space is, okay? It doesn't mean like these are fake spaces and real spaces. The word real, of course, comes from the set of real numbers, and you have seen for years now what we call the one-dimensional space or one space. Okay, this is simply R. That's a set of all reals. One-dimensional world, very flat, and in fact, there is not even a second dimension, which we will still call flat. But all you have is the set of all real numbers. In the two-dimensional space, we typically call this the plane. You have, of course, X and Y, right? So it's a set of all points that are ordered pairs of real numbers. The three space, what we often call the three space, more technically three-dimensional space, or space in general, is the set of triples, X, Y, Z, right? Where all of these variables are or do belong in the set of real numbers. Okay, so we will be studying basically 2 and 3 spaces in calculus 3. Now, theoretically, of course, you can go into any higher dimension, and some of that stuff will come up in your class like linear algebra, math 214. But in calculus 3, which is more of a application-centered, calculus class, we'll stick to 2 and 3 dimensions. Okay, what is a vector? Okay, a vector is an arrow with an initial point and a terminal point. Now, you may have you may have seen a more precise or mathematical or abstract definition of a vector, which you should do and study in Math 214. But in this context, or in the context of Calculus 3, a vector is going to be represented as an arrow with an initial and terminal point. All right, so we define, so you have all kinds of vectors, right? So we define two vectors to be equal to each other. This is a definition of equality of two vectors. If and only if they have the same magnitude and direction. So I am going to say this, even though this is not completely accurate. Vectors basically have magnitude, which is the length of that vector, and the direction. That's, of course, which way it is pointing. We call two vectors parallel. So this is the symbol for parallel. Okay. If and only if, any definition is really an if and only if type of statement, because we are trying to characterize exactly what we mean by that word. So U and V are two parallel vectors if one is a scalar multiple. And we'll talk about what this means in a minute. A scalar multiple of the other. All right. So if this is the vector V, twice as long, or that's not twice as long. Okay, let's say this is your vector V. If you draw one that's twice as long, that's 2V, and of course the direction is the same, so these are parallel vectors. Notice here these are not equal vectors because the direction is the same, but the magnitude is not. Now pay attention to this. Negative V is the opposite of V, so that V plus negative V is equal to 0. This is called the additive inverse. But are they parallel? Well, according to the definition, negative V is -1, oops, it is -1 times v, right? Is that a scalar multiple? Exactly, it is a scalar multiple where the scalar is -1. So even though they face the opposite direction, we call them parallel to each other. It may be a little counterintuitive, but that's the way we would define that. It's a more general concept of being parallel. All right, I should also mention what we call a position vector. Okay, what in the world is a position vector? Well, so every vector, because the vector is defined by its magnitude and the direction, not in its position, you can parallel transport a vector so that it starts at the origin. So it's a vector, any vector that starts at the origin. The origin could be 0 or 0, 0 or 0, 0, 0, right? And that's called a position vector. Every vector can be moved so that it will become a position vector, right? A vector that starts at the origin is called a position vector. Now you can add two vectors. How do you add these two vectors? I'm going to use my, can I use this? Yeah, I think I can use this. I have all these tools that are quite nice that I can use. Okay, so if you have U, that's my U, and if I have a V like this, okay, let's go back to this. All right, so how do you add vector U and vector V? Okay, there are a couple of ways of doing this. One is to draw a parallelogram where U and V are adjacent to each other. And then you draw this diagonal, which is called U plus V, okay? And so that is one way to draw this, and it is a geometric interpretation of this. Now, of course, there's another way to do this, the same thing, and that is to do U here. That was U, right? And then you can actually start V at the end of U. Sometimes it's called the triangular method or tip to tail method, because you're using the tip of the first one as the starting point of the second one. This is U and this is V, right? So basically the whole idea is if you are starting at this beginning point, you know, you start walking along U, and when you're finished with U, you start walking in the direction of V for the distance defined by V. And if you draw an arrow from the beginning to the end, this is U plus V. And of course, clearly, if you compare these two pictures, you can see they are exactly the same, right? Because if you add a few, well, a couple of edges here, this will become a parallelogram as well. The second one is called triangle method. I think your homework will refer you to using triangle method, and that's this. Okay. Now, later we will do this algebraically, in which you will not have to draw pictures, but that's how you can go ahead and do this. Okay. Scalar multiplication is the other. Basically, there are two operations, right? Addition and scalar multiplication. These are the two defined for like any vector in any vector field. But a scalar multiple is what I was talking about a little earlier. Okay, so let's see if I can describe this. Okay, so if I were given U, there's my U, okay, I can draw this twice as long, and that's going to be 2U, right? And so it's really nothing magical. Here's U, and so if you have the same direction, but twice as long, that's called 2 times U. So a scalar is basically a real number, okay? Anytime I talk about a scalar here, you can think of this as just some real number. Now there is vector analysis where the scalars can be any complex numbers like I or 1 plus I or something. But for our calculus class, we'll stick to scalars being real numbers, just real numbers. All right, so that's 2u. Now, if you go the opposite direction, okay, so this is, I didn't draw this precisely, but if you go the opposite direction, this is called negative u, okay, which, like I said, it is negative 1 times u. Now, remember, u plus negative u, I mean, this works just like, your integer calculation. If you add u plus negative u, then of course you get 0, right? But this 0 is not the number 0, okay? Because when you add a vector with another vector, you should not get a real number. So this is called the 0 vector, and 0 vector is just like the, well, sort of like an empty set or the number 0. You have to have it, even though you can't see it. And remember, just a few minutes ago, I said every vector has a magnitude and the direction. Well, the 0 vector does have the magnitude, the length is 0, but it doesn't have the direction, okay? So the fact that vectors do have direction is true for almost all vectors, except for the 0 vector. Okay, now subtraction is really not formally defined, but what we mean by subtraction is an addition by the additive inverse of v. Right? So u minus v is w. What do we mean by this, by the way? Oh, yeah, here's the analogy. Okay? You know what 7 minus 2 is? Okay, this is a really easy question for calculus students. 7 minus 2 is 5, right? But have you ever thought about the definition of subtraction? Yeah, we say 7 minus 2 is 5 because 2 plus 5 is 7. Okay? In other words, the difference is the number, so that if you add this number to the number you're subtracting, then you get the number that you start with. Okay, so that's the definition of a subtraction. And we are going to use a very similar method or the concept here. U minus v is equal to w if and only if w is that vector such that when added to v, it would produce u, okay? Alternatively, this is the same thing as u plus the inverse or the additive inverse of v. So it is okay to write u minus v as u plus negative v, okay? That's the same thing. But this will give you some ideas, right? So for instance, if this is, let's see, maybe I can use blue here. If this is my u, and if this is my v, you can go ahead and draw these pictures here too. All right, so if this is u, and if this is me v, where is the w? W is the vector so that w plus v is going to be u, right? You get that? That's the whole point. So keep that in mind when you try to figure out what that is. So v plus w has to be u. So the answer has to be this one. Does it make sense? Because, so this is, yeah, let me go ahead and write this so it'll be clear. This is w because remember, if you start here, okay, if you start here, you keep walking along v and then you keep walking along w, v plus w would be the endpoint here, which is u, right? And so that's the way to think about this. W is the vector so that when added v to this w, you get u. Of course, there's another way to think about this. And that's what I was kind of working on. Let's see. Let's go ahead and not have this. Whoop, what's going on here? Right. I'm going to try to make this into a nice thing with a color coding. All right, so my u was sort of like this. Okay, so my v is like this, right? Okay, well, this time let's do a negative v. Negative v, well, okay. Yeah, let's go ahead. Negative v would be somewhat like, did I have this? No? Yeah, negative v would be something like this. All right, let's identify these. This was u, and this is v, okay? And remember, I said u minus v is just like u plus negative v, right? So if you add u and negative v, then you draw a parallelogram like this. And this will define my sum of u and negative v, and that's going to be this vector here, right? And so what is that? Okay, well, this is, oops. It's really hard to draw this because there is this time lag, right? You get the point here. This big, thick arrow I drew is u minus v. And that's, of course, w in this notation. And so you can see that this is pretty much the same as this w you see over here, right? And so either way you can think of that's the way you think of subtraction. Okay. Now remember the zero vector, it is the set, well, it's not a set, it's a vector that has every component zero. Oh, by the way, I didn't write that. I'm not going to write this down yet. Let me just say zero vector. See, the vector is, because every vector can be moved to its position vector, which is the vector that starts at the origin that is parallel to the given vector. So you can assume that any vector can be moved in a parallel way so that it starts at the origin. So the zero vector would be the vector whose terminal point is 0, 0. And so I'm using this notation, which I should probably make a comment on. And so this is a mixed notation. That's not good. Let's erase this. All right. So when we write, or when we describe a vector in terms of its terminal point, because we assume that every vector it originates at the origin, and starts at the origin. So the terminal point actually gives you the what the vector is. And so if I describe this zero vector as with its terminal point, it's 0, 0 in R2, of course. Okay. And of course, it's 0, 0, 0 in R3. And notice here, I'm using what we call angle brackets. Okay, angle brackets are these things that are like, I'm not using the parentheses as I normally do to indicate points, right? These are called the angle brackets, and that's how we would describe it. And I normally use this throughout the course. So anytime you see an angle brackets, think of these as vectors and not just points in the respective spaces. Okay, so and so many times, instead of drawing pictures, okay, we can do these operations like scalar multiplication and addition and subtraction based on the coordinates, right? So if the vector u is u1, u2, remember this is the x coordinate, and this is the y coordinate, and so on. If you have u1, u2 as your vector u, and v1, v2 as your vector v, then the addition, subtraction, and scalar multiplication are very simply defined, all right? So for u plus v, this is u1 plus v1. Basically, all you have to do is to add these numbers component by component, u2 plus v2. Okay, and so for many of the applications, we don't even draw pictures, of course, because this is the most precise way of doing this. What is u minus v? Well, that's u1 minus v1, u2 minus v2. Okay, and then how about ku? Well, ku would be two-dimensional, and how do you multiply the vector 1, 2 by 3, for instance? Well, you just multiply the first component by k, and second component by also k. Right, so this will be ku1 comma ku2, and so that would be, this doesn't look like a u here, does it? Yeah. Okay, so that's how you can do these operations algebraically. All right, so that's the first page. Before we go to the second page, let's take a little break, and we will come back to this. All right.